Okay, I'll try to repeat anything that comes up that you can't hear. I'm going to open with a couple of questions and then we'll have some from the audience. So a lot of the feeling we got, this conference is called Machine Learning for Healthcare. And then maybe this last session we could call Machine Learning right now, maybe not for healthcare. But some of the questions that sort of were elicited by the discussion were about like definitional things about like what is machine learning, what is AI right now, where it might go. And at the end of Miguel's presentation, there was this comment on how even for prediction, it can actually be pretty difficult. And I think the audience and me would appreciate like a bigger discussion around, hey, the challenges that we face in predictions, like shortcuts, what's extra about causality and what should we pay attention to?
Well, I can start. Again, I think Miguel and I actually touch a lot of common points because obviously we both share causal background. And so what is actually, I think I touched a bit in my talk. Again, the causal inference, the fundamental, it's about counterfactual prediction, right? So it's what if question, what's gonna happen? What would happen if you do in another scenario? So it's not, as I mentioned, it's not just a two-arm prediction problem. Because if, okay, in an ideal case, you can do a randomized trial, then you have two groups, two patients, two group of patients that look exactly the same. Then yes, you can use your, because then you are using this magic tool of randomized trial to mimic, to kind of restrict the space you can do counterfactual prediction very well. So there you have some good basis. The two groups are very comparable to each other. So then you are basically use this good design to reduce the confounding issue. So again, when you do prediction, confounding is not a big issue because you just predict, you just put this input. In causal inference, the confounding is a big issue, and randomized trial, for example, is a gold standard to look after that. So, but in observational study, you don't have that. So that's what extra. And how do you then still achieve something like causal? First, as Miguel said, you need domain knowledge, because those domain knowledge will help you to actually to figure out what are the important confounders you have to look after, right? To adjust for in your model. So, but your machine learning algorithm would not know actually what are the important confounders. So that's the first thing. And then the second thing, even if you have confounders, if you have good confounders, the treatment group and control group might look completely different. Okay, so then there's in causal inference, if you do randomized trial, then just by the randomized design, the two groups will look the same. But if you are doing observational study, there's even if you have all this confounded information, two groups might still look completely different. And then you apply your fancy machine learning methods there. Still, the machine learning method, the model does not automatically take into account of that how these two groups look different. So then we have those traditional tools of matching or weighting, whatever, to make sure that the data, observational data I have, look as much close as possible to randomized trial. So those are the things, you need domain knowledge. You also need causal kind of, I would say, common sense causal inference. So those things are actually, I feel then once you have those data, have good, like with this, you look after the overlap or balance issue, and then with your domain knowledge to make unconfoundedness assumption as much as possible, plausible, then you're good to go. Like then I think that's extra. Then once you have that at that stage, then you combine the machine learning method. It will be very helpful.
And how does that like play with shortcuts? It seems like you need some domain knowledge for shortcuts. They're not exactly confounders, but they might feel like one. There's been a bunch of discussion about generalizing across different hospitals here and how shortcuts prevent that from happening. But it feels like that's even for like a straight prediction task, like detecting something in a chest X-ray, you need a lot of domain knowledge to even know like, hey, am I encountering a shortcut?
I think Miguel can maybe answer because he uses shortcut terminology.
Sure, I think that you put it very, very well, Fan. I mean, think about first about the randomized, before I talk about the shortcut thing. if we had a randomized trial, we have data from a randomized trial, we have data from an observational study. The way in which we analyze those two data sets is different in the sense that in a large trial, we don't have to worry about confounders. We don't expect to have confounders on all these things. So humans would approach the analysis differently. A machine learning algorithm would not. And this is probably the simplest possible example. The only extra knowledge that we have here is that the data from one data set comes from a randomized experiment and the other data set comes from an observational study. So if we had one way of telling the machine learning algorithm, look, this is a randomized experiment and this is an observational study, it would act differently. Now think of that at a much greater level of complexity, where if we have some way of conveying to the machine the causal knowledge that we as experts have, and the machine could combine that with the data analysis that can do automatically. If we could do that, we could make sure of one thing, which is that machine learning would not be worse than human learning. It might be better, it wouldn't be worse. What we cannot guarantee ever is that machine learning is going to be correct, because human learning cannot be correct for causal inference at this point. So the goal here is to make machine learning for causal inference better than human learning, because it can adjust for more things and in a better way. But that means that we're still not there, because there is this lack of an integrated approach. We can, at the very least, give causal structure to our analysis, and that's true for causal inference. That's also true for prediction. If we could convey, if we can give a deep learning, we can combine a deep learning algorithm with our knowledge that we should not use pixels in the X-ray that are about the hospital. So if we can combine those two things, then the deep learning algorithm will not be using those pixels, which a human would not be using. Now, is that enough to guarantee that the machine learning is going to be correct? No, because the human may be wrong. Maybe the human is not using those pixels, and there are many other pixels that should not be used, that the human is not even thinking that can be a shortcut feature. So we can do better, but we cannot guarantee we're doing correctly. And that's a very important difference with the way in which we have approached data analysis and machine learning in general, in which we can quantify how wrong we are, because we have metrics that tell us, look, this machine learning algorithm is classifying people correctly 99% of the time. We cannot do that for causal inference, and also we cannot do that for other uses when there are shortcut features, because and this all has to do with knowledge about the causal structure.
Great, thanks for that both. So again, both of the presentations were a little bit about definitions, about like what is AI in healthcare, what is machine learning. In Miguel, your talk, you mentioned a lot about like you can't do this directly from data, it requires knowledge. And then you talked about this like game setup where maybe you're building that knowledge from collecting a lot of experimental data. When you think about where that knowledge comes from, is it past data that should be incorporated? Does it exist somewhere? Like if you're a computer scientist thinking about this problem, where do you get it from an expert in a way that a computer could consume it? I think both are probably needed.
Right. I think that is a meta question, because one could argue that our extra knowledge comes from data. So in principle, we have an all-powerful computer, it could learn of our extra knowledge from data. And maybe that is what ends up happening. Right now, that is we cannot even think about that would happen. So it seems like that an intermediate step to improve what we're doing is to feed that extra knowledge in some way to the computer. Maybe in decades or centuries, we don't need to do that because the computer can learn that just by looking at the entire corpus of human research in the past. But that seems a farther goal.
Yeah, I think that's, and I think that's that's probably the question, the biggest question there, right? The data. So we get data, especially in the deep learning era, big data. We get a lot of data. So we have the, now the EHR data, for example, it's a big deal. And also before that, we have the health claim data and registry data, right? So using all of this, I think the key thing is still what I mentioned earlier in the design. So we can treat the data, if we treat data as is, we don't ask a question, where data come from, what's the sampling scheme, what is missing. So we should, if we want to do some causal problem, we always should first have in mind like what we want to get, right? That's a target estimate. Once we have that, we start to look at the data to say what is needed, whether this data actually is adequate for what I want to do. And I feel that's an interactive process that needs the domain knowledge and also some causal mind thinking. For example, causal people always think unconfounded. It's like, what are the important confounders stuff? So the knowledge is there, but that is without, the point is without some causal thinking there, then without framing the problem in a causal way, it is, if you just take the data as is and then apply the best even machine learning method, then you're still just, as I mentioned, garbage in, garbage out. It's like you don't know what you get. You need to start from somewhere. That is a causal setup. I mean, again, if you want to talk about causal inference.
Before I open it up to the audience, I'm going to ask you each for one positive thing about how machine learning, or like, I'll even make it more focused, how like deep learning maybe has made something new in causal inference possible, if anything.
Oh yeah, they are. I personally haven't done too much, but I know that, for example, if your outcomes, for example, are some imaging outcomes like the cancer. So if you want to see that if the tumor shrink or what, well, maybe that you can just use human eye, the doctor, and say this shrinks. But if it's more complex, then like current causal inference still use a lot of traditional methods, just use regression, whatever. So the outcome, like the phenotype, basically are much more, the phenotype, the current causal inference method focus on still pretty standard or pretty simple. When you talk about much more complex, like the image outcome or text information, like the text data information, right? Those kind of things, I can see like deep learning. You apply first deep learning, help you to do the phenotyping, and then you combine with a good causal inference methods. I think that there's a huge room there. I think some people already do that. So that's where I see that the future is like their causal inference think a lot. The field thinks a lot about design. How do we make sure assumptions? But in terms of the tools, there's still there's a lot of area to go, space to go. That the deep learning, the huge power that it can extract information from the complex data. That's what causal inference can bot.
We don't have a very compelling example yet of how deep learning may help adjust for confounding in a way that is clearly better than classical methods of adjusting for confounding. But I think that that's just a matter of time. I think that we will get there as the methods are used more and more, because once we are in the situation in which we have used expert knowledge to say, look, this is the set of possible confounders that we can use. And that set can be, we're maybe talking about a very high space. So we have thousands of values that are the possible confounders. And we can say there are really no colliders here and no instrument. So using these variables would be the best that we can do. I mean, that's the perfect setting for deep learning to shine, because say, okay, you have these thousands of variables, you know that the confounders are there somewhere. It turns out that if we use the right approach in a way that the inferential properties of our estimates are preserved, and we combine that with deep learning, I have no doubt we will be better off.
Great. Let's get some questions from the audience.
After learning analytics, my advice to everybody is you go to source. Who are you doing analytics for? For example, you're doing that for radiologists. Sit down with them day to day and look at what they want, not what you think, not what you saw in the old data. Because in the old data, we made lots of mistakes, and there are a lot of dark data inside of those images. Sit down with your radiologist or whoever you're doing work for. Let's see what they need. Then after that, go after it. I see that a lot of people, including Google and Amazon and others, they sit down and they think what they know. But we don't know. Look at your clients, what they need. Radiologists in California, they think different than the radiologists in Alabama. Their needs are different. Go into the source, whoever you do. One of the mistakes of the EHR is they build it for everybody, but it didn't work. Go talk to the physician and hospitals. They don't like it. CEOs, they like it because that's the money revenue. Go to the source. That's all I can advise you guys. Thank you.
Thanks.
It's a really interesting discussion. This is, I guess, directed towards Miguel, I guess relevant for both, though. I think you made the comment, I'm reading off a photo I took of the slide, so I'm cheating a little bit, that predictive algorithms do not directly guide decision-making, which I think I agree with, that for no other reason, for a practical matter. But it seems like there's a sense of autonomy in there as well. So in the sense of like, how do you think of what a decision is in the first place, what decision-making is? And in the case of, say, like bumblebees flying or an autonomous vehicle, like they're acting as independent agents insofar as anything else can be. So how do they seem to make decisions that alter the material world. So how does that play into senses of causality, prediction, and decisions?
So the distinction I was trying to draw there is that every time that you choose between two possible courses of action, which is making a decision, you are doing that because you think that one course of action is better than the other for whatever outcome you are interested in. So that is a causal inference problem. When you have to make a decision between A and B, and I'm going to choose A because if I turn left, it's better than if I turn right. If you are talking about a self-driving car or a bumblebee, or I'm going to give treatment A or treatment B because A increases the survival for this type of patient. So that's all causal. And when we are saying, when our analysis is not to help that choice, our analysis to tell you, look, this is the pattern that exists. This is, if you have all these inputs, I can tell you who is at the highest risk of heart disease in the next year. That's not causal. There is no choice. I'm telling you what your risk is. That doesn't directly help decision making in the sense that it's not telling us what to do. It is telling us that the decision needs to be made because this patient is at a very high risk. Under the assumption that we know what to do if a patient is at very high risk, we can argue that that mapping is helping decision making, but only if you know what to do. If you knew what to do before doing this. And I think that distinction is important because a lot of machine learning talk is about better decision making, but then a lot of what is done is about mappings, not about helping to choose between those two things. Let me know if that answers your questions or I misinterpreted.
In the case of like autonomous vehicles that do exist, do you think that they're making decisions about whether, they're making left turns, right turns, stopping, things of that nature? So how do you map that kind of thing to what you're talking about?
They are doing causal inference. They are doing causal inference, but that is only one step farther from games, in the sense that when you are making causal inference in a setting in which we know a lot of the rules of the game, we know the laws of physics, and we have sensors. So what is left there? Well, the random human who may jump in front of the car. And that's not something that is part of the rules of the game. So we have to have some assessment there. But self-driving vehicles are it's a relatively simple system, despite it's hugely complex, of course. But we're talking about a relatively simple system compared with healthcare. Compare to questions whether I brake or I don't brake now, or I steer right or left, which are causal questions, are much simpler questions than do I treat this patient with A or B, given the characteristics of the patient. And so there is a qualitative distinction there, and that's why deep learning with some rules-based and a lot of causal knowledge in the form of the laws of physics can help a lot with causal inference for self-driving vehicles, because the problem is relatively simple. And please don't take this out of context. It's a hugely complex problem, but it's relatively simple when you compare with something that has to do with a human body.
It's one all the way in the back.
Can I go ahead?
Oh, you
or-
can go ahead in the meantime.
I guess it's a question maybe for Fan. I guess Miguel can chime in too if you have like insights. You want to share some insights. I guess when you mentioned something you talked that it's much better to have a better design to begin with than worry about in another stage. I was just wondering whether you can maybe elaborate a bit more on that. I guess in the real world, obviously randomized controlled trials are the best design that we have, but a lot of times that may not be plausible. And so what will be some of the, either on conceptual level, what the good designs are, should be, or maybe some concrete examples to illustrate that. Thank you.
Yeah, that's a good question. So again, by design, we actually mean more broadly. It's not only the design to collect the data, but it's also include the thinking of the S-demand and assumptions that stage. But so let me, so think of an example. It's a I can give an example like in the vaccine study. So often, like for example, in the COVID, I need to elaborate that, but in the COVID vaccine study, so I think DCI Duke got a big contract from either NIH or PCORI to do the vaccine monitoring and the effectiveness of the COVID vaccine. And so I think when they designed that, there's just a lot of, so then they're thinking of actually, they collect the data from healthcare professionals. And so they, like when they design these how to collect the data, so one key point, I don't know whether they consider, but I mentioned that like the first didn't consider is actually the timing. So because like in the setting of the COVID-19 case, it evolved very fast, right? So new vaccine come in, and like even after 5 months, the way we treat COVID-19 is very different from 5 years ago, or 5 months ago, and also the availability of the availability of the vaccine, and a lot of that kind of parameters in the design. I didn't participate in design that study, but I remember that it turned out then, if you're just thinking of, okay, I will follow up 10,000 healthcare workers, and then follow up what their outcome would be, then if you just simply do that, actually a lot of this kind of nuances of the timing and everything is lost. If you don't consider that, actually you don't collect enough information, like the possible confounders. And so I cannot give more explicit because this is just someone discussed with me when they get the data, then they realize actually a lot of important information they didn't collect. So I feel that if we sit down, like if some causal inference experts maybe sit down first with the trial designer, probably then you think, okay, what is our target estimate? Is that average treatment effect? Average treatment effect on what is your target population, for example? And then what is a time kind of the time involving will the time play, what kind of role of time plays in terms of confounding? And then maybe if we start to think of that when we first design the data, then probably the data will have less trouble. We will have more like relevant confounders. But yeah, in general, it is very, and there are many that kind of designs, and there's no good design or bad design. Even people say, oh, use IV. Okay, that's a good idea. But then if you end up with getting a bad IV, then your analysis is not good. So I feel that, yeah, it's a general idea or general kind of principle that designs Trump analysis. So think of the data acquiring, or I use Miguel's terminology, would be know more about how the system works, right? As much information, domain knowledge about the system works, and then come up with a design. But it's really highly case by case. So it's very hard to say that before each study, what would be a good design. It's really, you have to talk to the domain scientists or the clinicians, and then to figure it out. But it's a bad practice if you first collect the data without thinking of the problem, and then once you get the data, it's very hard to fix it.
We have time for
Yeah.
one last question in the back.
Yeah, thank you both for the talks. I had a question specifically to Dr. Lee about kind of, I guess a major theme of both talks was how you marry deep learning and causality kind of a bit better. So I was wondering, for the design stage specifically, is there kind of work looking at for deep learning to automate some parts of that? So for example, the design of a causal graph or something like that, is that something where deep learning could have an impact on the design stage of causal learning, or is that something that would need human intuition more? I think that it was sort of implicitly answered in the question before, in that it would be better to have a human design it all the way through, but I just thought I'd ask you anyway.
Well, I mean, if you talk about the causal graphs and things like that, to be honest, I don't think a way of, without kind of domain knowledge, how do you deep learning automatically learn the design knowledge, the design stage almost just by definition actually contains a lot of domain knowledge, or how the system works and stuff. So I find just sitting here, I find it's hard for me to come up with a scenario that a deep learning model can help with that stage. If you're talking about causal graph, again, first of all, whether we can learn causal graph from pure data. I personally think that it's impossible to learn a causal graph from data alone, use whatever algorithm. That's just impossible, because the causal graph, it's about all the errors, all the causal connections. I mean, that is domain knowledge. I don't see that how, without knowing that, you can actually magically use machine learning models to come up with that info. So I don't see it.
All right, let's thank Miguel and Fan one more time.